So last time we looked at how to find the magnetic field from current carrying wires and loops, and we had the magnetic field from a wire was mu naught I over 2 pi r, which crashed to the negative 7 I over r. And then we also had the magnetic field for a loop was equal to n mu naught I over 2r. So we just practice using those and how to calculate magnetic fields from different sources. Okay, so today what we're going to do is we're going to start looking a little bit at magnetic forces on different things. So we're going to start looking at forces from magnetic fields. Now, we're going to start with what you guys took last year. Last year you guys took, you have a wire or something like that, and it's got current going through it. There's my current. And then you guys had magnetic fields like this. And what you guys did last year was the force was equal to BIL sine theta, something like that. Okay, now the thing is the force only existed when you actually had a current running through the wire. So we talk about the force being in the wire, but the force isn't actually on the wire itself. The force only exists when the current is flowing. So you have to have that current flowing in order for there to be a force, which sort of means that the force isn't really on the wire. The force is actually on the moving charges that are actually going through the wire. Okay, so it's not really a force on the wire, it's the forcing of the charges that are moving, because when the wire is in the magnetic field, you get absolutely nothing. It's only when the charges are actually flowing from one place to another that it actually has a force. So if we go back to, actually learned this in grade 9, but current is actually defined as the rate of current flow, or rate of charge flow, delta Q over delta T. So if we take that and we put that into expression, we can see something else here. So if we put the magnetic force is equal to B, and put delta Q over delta T in there, times the length sine theta, there we go, something like this. So if we do that, two things go together here very, very nicely. You guys have been doing it for a very long time, it's just not necessarily obvious. Down here we have time, and over here we've got length, which is just a distance. So you actually have distance divided by time, and that of course gives you speed or velocity. So really, you can replace the L and the T with speed or velocity. So if we do that, we have the force is equal to B. We still have that delta Q in there. And then these two actually can be replaced with V sine theta. So this is how you can actually calculate the force on the wire. Now you can see the force is actually on the charges, the moving charges, and right there the V, they have to be moving. So the force is not necessarily on a wire or something like that, so to speak. The force is actually on moving charges, and the charges are just contained within the wire, and therefore the wire goes along for the ride, so to speak. Okay, so if we sort of let's rewrite this out a little bit. Typically the way it's written is, the force is a magnetic force. And most people drop the delta here, and you'll typically see something like this. QVB sine theta is typically the way it's written out. And it is velocity because, the way the force goes is determined by which way the charges are actually going. If they go one way or the other, you'll get a force in opposite directions. So you actually have velocity or not the speed, okay? And for what most of the stuff you guys will do, typically this is at 9 degrees, so it's going to be equal to 1, just to make things a lot easier. Otherwise you get into other types of motion we're going to get into. But so typically to find the force on a charge in a magnetic field, forget the wire, you just do Q times V times B and calculate how much force is on it. So it's pretty straightforward, and you've actually sort of did it in a hidden way in grade 11 when you're using the force is equal to BIL sine theta. But now we can remove those charges. We can remove the electrons, we can use protons, we can use any kind of charge we want, put them into a magnetic field, and you guys can calculate the force acting on them. Okay, so let's practice that a little bit and sort of show you how this works and get to some scenarios. Okay, so let's start really basic here. Let's just have a magnetic field. Let's say we got a 0.14 Tesla magnetic field, and we'll just bring in a proton coming in at, let's go with 76,000 meters per second, and let's use something really, really simple. Okay, so let's just find what is the force on the proton. Okay, really simple. Okay, so to calculate the force, magnetic force is QVB sine theta. It's coming at 90 degrees, so that's going to be equal to 1. You have the charge of proton, you have the V, you have the B. We just have to multiply those three things together. And if we do that, I believe we get 1.7 times 10 to the negative 15 newtons. So that's the force on the proton, just that straightforward. Okay, so let's try something else. Let's let's draw a magnetic field like this. All right, let's use an electron. So here comes the electron, and let's say the electron's coming in at 8.4 times 10 to the 6 meters per second. It's coming in there, and let's say the electron feels 1.42 times 10 to the negative 16 newtons. So what is the magnetic field? Okay, so just using the same expression as before, we've got the force, we've got the Q, we've got the V. B is what we're looking for. So we're looking for the magnetic field. Sine theta is going to be equal to 1. I'm not even going to bother writing it. So that would be the force divided by the Q and the V. And we just have to punch those things out. So we've got like the 1.42 to the negative 16 and divide by their two quantities, and we will have our magnetic field. So I think that should give us like 1.06 times 10 to negative 4 Tesla, so something like that. Okay, so that's the basic way to use the expression. Typically we don't have combined forces. Typically we don't have multiple magnetic fields and the charges. That's not like combining electric forces where you have a few charges acting on it or a few fields acting on it. It's really like one charge in one magnetic field, and that's basically it. Okay, so I'm going to show you something else involved with this, and that has to do with the direction of the force, because of course force is a vector. Got to look at which way the force is actually going, and this is going to be a little bit different than what you guys have had before, so we're going to have to poke at a couple other things here. So before we get into the actual direction of the force, we're going to do a little side note here for a second. One of the first expressions you guys ever did is you guys would calculate, like displacement is equal to time times velocity. And how did you know which way the displacement was? Well, whatever direction the velocity is, that tells you what direction the displacement is. The same thing when you guys do change in velocity is acceleration times time. It's the direction of the acceleration that tells you the direction of the change in velocity. When you guys do F equals ma, it's the direction of, even to go backwards, the direction of the force gives you the direction of the acceleration and vice versa. It's all the same type of thing. So you've always had two vector quantities, and one of them tells you the direction for the other. Well, this expression is a little bit different. This expression, you have force is equal to QVB sine theta, but here you have not one, but two vector quantities. And when you have two vector quantities, which one tells you the direction that should be used for the force? One doesn't take precedence over the other one. Like the velocity vector is not more important than the magnetic field vector or vice versa. It doesn't work that way. This one gets a little bit different. Now, because you have two directions of the velocity and the magnetic field, and one can't take priority over the other, the force cannot be in the direction of either one of those two, which means if the magnetic field is going one way and the velocity is going another way, the force can't be in the direction of either one of those two. It has to go in the third direction. So that means that this has to actually be in the third dimension compared to the other two. Now this sounds fancy schmancy, but just hold on a second. Okay, So it has to be in the third dimension compared to the other two. One can't take precedence over the other. Now we're going to take a little nerd moment here on the side. One thing this expression has is right here. You're multiplying two vectors together, which you guys have never actually done before, whether you realize or not. Now, when you actually multiply two vectors together, that is actually called a cross product. And it's actually written as velocity, the big X, and a magnetic field like that. That's how you show a cross product, which means the direction's involved. Now, it seems like a really, really big timesing sign. It's one of the reasons you stop writing timesing signs when you do more advanced math, because it's a cross product. When you have a cross product, you multiply the two values together, but the answer has to have a direction which goes in the third dimension. An example of this is when you guys were looking at electric flux a while ago, and we had an area, and we said that the angle between the two was not between the area and the field, but we said that the surface actually had a vector coming off it called the normal. Well, that normal is actually a result of the cross product of finding and using the two dimensions of the area to calculate the actual area itself. So when you do length times width for this rectangle, they're sort of directions, and the answer, the area, actually is a direction in the third dimension. I know this sounds like nerdy weird, but that's just the way it is. So you guys can take more of that in university or college or something like that. So that's where that cross product kicks in. So the force vector can't be in the direction of the V or the B, it has to go in the third direction. So for example, if the velocity was going sideways, the magnetic field was going up and down, the force couldn't go left and right, the force can't go up and down, the force would either have to go in or out of the screen, one of those two. So the force vector would either be in, which would be, you'd write an X, or coming out at you and you draw a dot, just like when you guys have drawn magnetic fields and stuff like that. So there's three dimensions involved, okay? Now, there are different tricks and things that are used to actually remember this type of stuff, but in the first time you guys looked at this in grade 11, you guys learned about right-hand rule number 1 to find the magnetic field of a current carrying wire or something like that. Well, to do this we are going to use what's called right-hand rule number 2. And it is used to find the direction of a force of a subatomic particle within a magnetic field. Okay, and there's different variations of it. I'm going to show you my favorite one that I like to use, and I will show it to you guys in the next video, and then we can start looking at the direction a little bit. Okay, but that's sort of like the basic idea of and the basis behind how some of this stuff works and why the force is not hard to calculate for magnetic fields, but the direction is a little bit different to find. But we'll look at that in our next video.